This video is being recorded for Physics 306 Electronics, and the topic of discussion is difference op amps. Difference op amps take two input signals and output the difference between them. Applications of them typically include measuring small voltage changes in sensors which are in noisy environments. They eliminate interferences. As you can see in this image, we have the real-life circuit used to gather the experimental data. We have four resistors. One of them is hidden under here, under this resistor. And we have a MIDAC board which used the arbitrary waveform generator to deliver two input voltages, V1 and V2. To measure the data, I had one probe connected to the end of RG, connected to ground, and the other probe connected to this orange wire here, coming out of the output. Here's a circuit diagram. As you can see, there's four resistors and two voltage sources. This is a negative feedback inverting op amp. And to calculate V out, I used the method of superposition and nodal analysis. So I turned off V2, completely ignored it, and just carried on with V1. And I received IR1 is equal to IRF. This is because we have a current coming from V1 across R1, flowing from left to right, and then we have V out, another current flowing from right to left across RF. Two currents in a negative direction, in opposite directions. So we have them equal to each other but negative, and then solving for V out, we have a negative RF over R1 multiplied by V1. For the V2 contribution, we have V positive is equal to V2 multiplied by this voltage divider, RG over R2 plus RG. So we have the voltage drop across R2 is equal to V positive. So we just do the voltage divider for R2 multiplied by V2, and then similarly for V minus, we have V out multiplied by R1 over RF plus R1, because we want to find the voltage across RF, which is equal to here, to V minus. And then we assume ideal conditions. So the gain is infinite, and therefore V positive would be equal to V negative. And then we just solve for V out. Then we apply superposition, so we just add these two equations together to get the total V out. And as you can see here, we have this difference equation. So the subtraction sign signifies the difference op amp, because you have one input being subtracted by the other input to get one singular output voltage. Theoretical results, I kept everything constant with the simulation, and when I plugged everything in, I got negative 12.95 volts. Here's the simulation, also negative 12.95 volts with everything the exact same. Here's the data. I had 6 good experiments where the data was below 5% margin of error. And as you can see, the experimental data, the theoretical data, and the simulation data all lined up pretty nicely. 5 different examples. The reason why I didn't include percent difference between theoretical and simulation is because the margin of error was very insignificant, but differed by only 0.005 or 0.001, and the margin of error would just be accounted to round off error, human calculation. Reasons for the experimental margins of errors, was because the resistors didn't have the exact ideal ratings on them. Some of them had higher tolerances, which led to different voltage drops in the calculations. And also the breadboard and wires may have also had some hidden inductances or leached some current, which leached some current out of the experimental data. So yeah, thank you.